This is kind of an old story for me. In fact, some of the work I'll show here is even things I did for my PhD years ago. In fact, I was commenting to Larry Griffiths. He and I shared a AISC stage like this one back in 1988 talking about composite structures. So part of this talk begins there, but there's been research over the time and developments in practice that I'd like to kind of relate to you today. Many people have contributed over the years, many kind of sponsors including AISC, and many students and practitioners have contributed, but most recently Paul Cordova, Sami Mahani, and Ryoichi Kanno, most directly to what I'm talking about here, but others as well. So certainly what I'm showing is not all my own work, many contributions. So I'd like to, just to keep us on track here for this long talk a little bit about background and applications. One of the key things about these composite frames is the moment transfer between the concrete column and the steel beam. Talk about that a little bit. And then a good part of the talk I'll be talking about a large validation test we did cooperatively with researchers in Taipei in Taiwan. So we'll be talking about the testing and analysis to validate these systems, and then talk a little bit about the future. These mixed concrete systems really came into vogue or been developed in the 1970s and 80s, particularly in the work going on in Houston at the time. And I think that's important to recognize because two things were happening. There was a lot of building, well, three things. There was a lot of building going on, number one. And I think Houston was one of those markets that was kind of a new city being grown up. So things like that might have impede composite construction, labor union practices and so forth were not down there. So the engineers were trying a number of new things. And I think actually Fazler Khan, the folks at SOM, could be credited with maybe some of the early ideas, and then many other engineers innovating on top of that. One of the earliest types of systems here were, up until this point, tall steel frame buildings, but recognizing the advantages of starting to use reinforced concrete to resist lateral loads. So in this type of system here, it's basically a concrete perimeter frame that's wrapped around a steel frame inside. That didn't last too long, though, because the designers saw, and this is one Larry Griffiths in the audience here from Walter Moore and Associates, began to look at these systems and recognize that concrete was doing the most good in acting in compression in the column members, and on the flip side, encasing the whole steel frame in concrete, particularly the beams, was rather burdensome from the constructability standpoint. So developing then frames, moment frames that consist of reinforced concrete column and steel beams. And this then brings in the important question of how we connect the beam and the column, because a lot of our codes of practice and standards are used to dealing with one material and not the other. This is a picture of the construction of this building, showing a little bit of the idea of how the building goes together with this tree form type of construction, the columns being cast in place. You can see this is a low seismic zone, evidence from the relatively minimal amount of ties that are used in this. Because indeed part of the progression and part of the development that's gone over the years is started to look at this applications to seismic. This is another, about 8 years after the first one I showed you here up in Minneapolis by CBM engineers, kind of a mega system, a large Virendale lateral system on this that uses again this composite frame with the beam column connection that you see here. This is a close-up view of that. And I wanted to show this in particular to start to see the additional reinforcement being put in here, but also as we started to better engineer the connection, moment connection between the steel beam and the reinforced concrete column, and thinking about how we get the force transfer between the two, start to specifically detail some key elements. One of those, and this was borne out in some tests that I'll show you a little bit later, these face bearing plates. So as that beam, as the top flange starts to push into the column, these plates bear against the concrete and start to develop diagonal compression struts. Also this vertical joint reinforcement. These are reinforcing bars that are connected to the flange with some sort of mechanical coupler. It could be a welded or a welded screwed type connector. So these were the things in these systems that were starting to enable this large moment transfer between the steel beam reinforced concrete column. This is just one more example of the time. This is early 90s, just to show kind of these ideas were spreading. This was by the Cantor Group in New York, a building that was built in Philadelphia, 1991, using a similar composite moment frame. So if we look at this construction practice that evolved over about 10 or 15 years until the early 90s, the evolution was a variation of steel construction. So tall steel office building have a lot of attributes in terms of the long spans, the flexible floor system, and so forth. But the idea is that there's were advantages for these higher buildings, and depending on the market conditions, the relative price of steel and concrete, to start to use this composite action, and in particularly the composite action in the columns. The economy of concrete in vertical members being easy to place. The concrete does the most good when it's in compression. The speed of construction, I'll show a slide where the construction of the steel and concrete were staged to allow the building. So this was an integral part to make these systems economical to build. And related to that is the versatility in design and construction. And in fact, I think the most important thing looking to the future about these composite systems is that they provide us new opportunities to evolve different forms and practices, and I think really to look for the economies by combining these two different materials in interesting ways, I think is the biggest potential these composite systems have. There were some disadvantages that continue today. Mixing of construction trades, and that's why I emphasized, I think, the places you see these things being pioneered are kind of newer cities, newer regions where there's less tradition in the construction trades, more willingness to work together. And lack of design standards and guidelines. And I think this is an area, though, where over the past 20 years we've made good headway to make these systems, there's more guidance out there for engineers, and also they're better recognized in the building codes. And interesting is that while these systems were being developed for tall buildings in the US, at the same time and independently in Japan, there was a practice, and this is where the name RCS comes, where they're using very similar systems but for low-rise construction. These were used in shopping centers and offices, and this is actually starting to replace buildings that otherwise would have been reinforced concrete where they wanted to go to longer floor spans. And as of a few years ago, there's about 100 of these buildings that had been built in Japan. An interesting difference in Japan, they used different multiple construction sequences. They started to use precast columns, work well for low-rise, not necessarily high-rise, but also different types of cast-in-place using the reinforcing bar cages as erection columns, and I'll compare that in a slide, the next slide. Another big difference in Japan, right from the start, they were using these systems in high seismic zones, where again I would emphasize in the US being first developed in Texas, very low seismic zone, kind of less encumbered by building code provisions and so on. And again, the idea is to take some of the precedent of using these in high seismic zones in Japan and seeing how we could build on that to introduce them here in the US for high seismic zones. So just to compare the construction schemes, this is the one that is common in the US for the tall buildings, building your steel building with small steel erection columns coming back and later encasing the columns. And again, I don't show it here, but this would typically be staged over about 10 stories of construction. In talking to some fabricators, even here in the US, one of the drawbacks of this system is you kind of are buying two columns. You're buying a steel column and then a concrete one that wraps around it. Some of the Japanese construction companies have pioneered systems, as shown here on the right, where they're actually using these reinforcing bar cages as the erection element. Now they don't just take an ordinary cage, they'll actually take some devices here and make it it's an engineered reinforcing cage, if you will, engineered for the construction loads. And I think it's systems like these that really help promote the economy of making these competitive against a pure steel or pure reinforced concrete system. The precast systems that I mentioned, this is an example by Shimizu Corporation. There's been others in Japan as well that have used this. And I think it's pretty evident to see the idea to take precast units where the cast off site, the precast column, and the beam cast integrally with that, and then having splices, grouted splices for the columns, and then bolted splices to put the beams together. And again, this works very well for low-rise. Due to the size of the columns and hoisting and transportation, there's only so far you could go as your column sizes get bigger. Now I think if we step back a little bit, the systems were originally developed for, because of the economy at the time, relative prices of steel and concrete, the effectiveness of these in tall buildings. But now if we step back and say what's another advantage to them, particularly since the Northridge earthquake, where in California we had some unexpected fractures to beam column connections in steel frame structures, where the fractures occurred where we welded the steel beam to the steel column, is that a key advantage that these RCS systems have for seismic design is that the steel beam runs continuous through the column. Reinforcing bars in the column run continuous by, so thereby we avoid splicing either of these two members at the most critical location. So then we're doing the field connection out here some distance away from the column. So this has a key advantage to be continuous, the beam's continuous, avoids welding at the location of maximum forces, and tests, as I'll show, have borne out that this connection has stable hysteretic behavior, something we're looking for in seismic design. Now, in terms of seismic design standards, there's been a lot of work, and I won't describe all the development, but just summarize where we're at today, is that kind of in different, seismic design occurs in different tiers, but if we start at the top with the, now the International Building Code, which is with the seismic provisions really built upon the ASE 7 document, these were provisions that outline the seismic response factors that you need, the so-called R factors, that really acknowledge that there is something that we'll call a composite moment frame. These provisions were first introduced in 1994 in the NIHER provisions that serve as a source document for ASE 7. Now, this document refers to the AISC seismic provisions that has a Part 2 on composite. And what this Part 2 does is it really lays out requirements for when you want to build a composite frame, just how you would detail the steel beams, the columns, and requirements for the connection. Now, this document doesn't repeat. Much of what is in these moment frames is actually things that are covered in the steel specification or ACI, the concrete specification. So these Part 2 seismic provisions, they'll outline some general requirements, things for strong column, weak beam ratios, and so forth. But for detailing of the steel beams and the concrete columns, or they also permit composite columns, this document then points to ACI and AISC for the specific requirements for detailing the members. Now, the connections, again, that's a key part to these, is that there's some guidelines published from ASCE. Originally in 1994, some of the research that's been done since then, we're just putting together an update to that that's going to cover more configurations and so forth. So there are design guidelines out there. I thought before going further with more of the details, just to show a quick design example. I won't show all the details of how we designed it, but just what kind of structure you might end up with. So this is a 20-story moment frame example. The building we're looking at, it's modeled after one that was a 20-story building that was kind of a case study done as part of the SAC joint venture. This was the project that was done after the Northridge earthquake to look at the seismic safety of steel frame buildings. So we've designed this perimeter moment frame structure in a high seismic zone. If you're familiar with the seismic codes, with an R factor of 8, so we're relying on a lot of ductility in this system. It's kind of a mid-rise where we felt these composite systems are competitive with pure steel frames. And the controlling design criteria, strength typically in the beams, the columns are controlled by the strong column weak beam requirement, and sometimes in the taller buildings drift requirements will also govern, but usually it's these first two requirements. So if we just compare these two frames, and again it's a perimeter frame system side by side, the framing system is actually quite similar, the key difference being in the columns. So you have beams around the perimeter, W24s to W30s, and if you average that out, the moment frame steel averaged out over the floor area represents about 3 pounds per square foot of steel. The columns in the steel system would be W24s, about 4.8 pounds of steel. So we're replacing those with columns, concrete columns, that are 30 by 35 or 30 by 30. And then the gravity framing system is here. So if we contrast these two and say, what have we gained or what's the difference? We've replaced some of the steel that's in columns, typically some very heavy shapes that might have lead time issues with the reinforced concrete. But again, the other thing we've done is through this composite connection, and let me show that here, is we've avoided a lot of the problems associated with field welding of these moment connections. And again, especially since the Northridge earthquake, with more requirements on quality control, weld toughness, and so on, this has advantages. So this is the composite beam column that would be used in that frame. The steel beam runs continuous through the column. And in order to get the strength to work, the size of the joint is really dictated by the member sizes. But in order to get the strength to work, that is to develop plastic hinging in the beam, transfer that into the column, it's relatively easy by the addition of these band plates on top and these face bearing plates together with some ties in the joint are kind of what's required to make that happen. Now we don't just put those on there, there are the guidelines I'll talk about, the ASCE to proportion those plates and do the calculations for joint shear and so forth. So that's what I'd like to talk about next. So over the time, in fact, I worked on this back at UT Austin back in 1985 along with Takir Sheikh, another PhD student at the time, and that was some of the first work done in the US, and there's been continuing work both in the US, Japan, other places around the world, focusing on this, what we'll call this through beam type detail, focusing on transfer mechanisms, how do forces get from the beam into the column or vice versa, the details, and we looked at many different details over the years, but the ones that emerged as most effective and easy to build are the ones that are shown here, the steel band plate and these face bearing plates, and a whole host of kind of other detailing issues that you may want to use. For example, the use of high strength concrete in these joints. So there's been tests, and these are some of the names of the work we did in Texas, some more work at Cornell, University of Michigan, Texas A&M, groups working in the US. Parallel, and in the early years we didn't know we were each working on the same projects, but soon we found out about that, so there's been cooperation between US and Japan on this, some of the names that are shown here. And this really culminated in these design guidelines first published in '94 and currently being updated. Just a few slides to show the kind of testing that was done. This was some of the early work at the University of Texas, and you can see testing relatively large-scale beam column subassemblies, the concrete column and the steel beam. This just shows how one of those joints is put together, some of the damage that occurs, and in these early tests when we wanted to figure out how strong the joints were, we purposely designed the beams to be very strong so that they would not yield and to force all the damage into the joint, because that was the only way we could figure out how strong the joint is and thereby develop design guidelines for that. Of course, when you're using these for seismic design, you actually proportion the joint to be stronger than the beam. Okay, so these tests were a little bit backwards, but we needed to do that in order to figure out how the joint is behaving. But this shows if there's an angular distortion of 1%, might correspond to 1% drift in your building, this would be the kind of damage that would occur in the joint. And out at 5%, we start to spall concrete, but it shows the important role that these bearing plates have and also these ties have at kind of holding the concrete in there so it could maintain itself to resist. Basically, we develop diagonal struts as this top flange tries to push through the column with these bearing plates. We develop diagonal struts, and you see that in some of these cracks that are shown here. And so if we think of the different modes of failure that could occur in a subassembly, those are shown here. The joint failure, again, this is the one we forced by making strong beams so we could investigate the joint. At the other extreme would be beam hinging, or potentially a mixed failure where you get some hinging and some failure in the joint. Although it turns out with the details we have now, it's relatively easy to make the joint stronger than the beam and to get these beam hinging details. This just shows a comparison of that. This on the left is shown a specimen where this is a regular rolled shape where we got hinging outside, a little bit of cracking in the joint, but not much. This was a case where we used a built-up shape with very heavy flanges such that the beam didn't yield, and we get the failure, the joint panel shear. And these are the hysteresis curves that go along with those, the beam hinging and the joint shear. The important thing about the joint shear, it has some pinching behavior, but it actually holds up fairly well, up to fairly large deformations on par with those that we would get through beam hinging. So even if failure does occur in joint shear for seismic design, it's still holding itself together fairly well. Now the design guidelines, I don't have time to go through, and maybe this time of day you wouldn't want to see all the equations, but just to give you a flavor of kind of the way they work, we kind of have to dissect the joint and to think of the force transfer that occurs when you put a moment in shear on the beam here, how that turns into a moment in shear in the column. And some of it occurs in what we call this inner panel. This consists of the steel beam and the concrete that's held captive behind these face bearing plates. The other part is the rest of the concrete that surrounds the joint, the outer panel. And there, you can see by these red and the blue arrows, there's force transfer that occur between those two. That inner panel, there's kind of two predominant modes of failure. One that's called a bearing failure, where the beam is relatively strong and causes crushing, kind of rocking inside the concrete, if you will, and gaps opening up. The other would be a panel shear failure. Now this failure is one that's more commonly that we see in steel structures where we have panel yielding. In this case, indeed, we do have the steel panel yielding, but we also have this compression strut that's being developed in the concrete. So as this moment comes up this way, the flange pushes to the right. Face bearing plates are here, allow this diagonal strut to develop, and that assists then the steel web to resist the shear. So if we think of normal steel buildings, oftentimes we'll have to add doubler plates or diagonal plates to handle that. Here the concrete is naturally helping us out in that regard. These are a couple of pictures of a joint that's failed in panel shear and one that's failed in that bearing mode. So this gives you this slide gives you an idea of the different kinds of details that were investigated in testing over the years. First test for a plain steel beam going through the column. We saw early on adding these stiffener bearing plates helped out. We extended them above the top. We added that vertical joint reinforcement. And finally, the notion of the steel band came in, because aside from other things, when we put the steel band in, we could then eliminate the reinforcing bar confinement in that region. The band takes that place, which really facilitates both the erection and then the placement of concrete. And again, the ASE guidelines that to proportion this basically go through looking at each of these failure modes in the inner panel and the outer panel, and carefully looking at what's going to govern, and thereby come up with the design, figuring just how, in terms of bearing plates and the band plates on top, how thick they need to be, and weld detailing and so forth for those elements. So these are the two joint failures. The purpose of this slide is to point out that we started in 1994 with a set of design provisions. There's been research since then resulting in some provisions that are being updated, in fact finishing up this spring. These slides on the right just show that these are comparisons for panel shear failure and for bearing failure. If we take these design guidelines and compare measured values to calculated values, the hollow circles here, the open circles, are the ASE guidelines from 1994. These were purposely a little bit on the conservative side. This value of 1 means we have perfect match between the experiment and the nominal strength values in these design guidelines. So we were somewhat conservative, intentionally so, with limited tests early on, but over the years with more tests, we've got these up close to a mean of about 0.9 and also reduced the scatter somewhat. And I don't have all the pictures here, but these are the joints by which we're plotting data for. But these cover a whole host of variety of different details and geometries and so forth. So we feel we have a real handle on making these beam column connections work. So what I'd like to talk about now is a large-scale frame test that was done to help, especially for seismic design, to demonstrate not just that the joint works, but when we put this whole system together, how well it works. This was a large test. We did this cooperatively with folks in Taipei, their National Center for Research on Earthquake Engineering. This gives you an idea of how big their lab is. Actually, my student that spent a better part of a year there, when he gave me this picture, I said, something's missing. We got to get a sense of scale. So I Paul put his picture in there. So you can see this is basically a full-scale frame, tremendous laboratory facility, 4-meter story heights. The beam spans were compressed a little bit. The lab wasn't long enough, say if we had our normal 30-foot spans or 25-foot spans, compressed a little bit, but otherwise developed to concrete column, steel beam. We also had the floor slab there, and we were careful on how we introduced loads into the system. Now, before going through the details of what we tested, I wanted to talk a little bit about the reasons, what was the rationale for this test, because it was not an insignificant undertaking. The first thing is a proof of concept. We could tell people these things work for seismic and how to build them, but this is a proof of concept to show that we can do it and test it. There's also a number of behavioral effects that we can't understand fully from subassembly tests. I showed you before the subassembly of a beam column joint. We could add slabs to that, but we never see the whole indeterminate nature of the system until we put together a frame of the sort I just showed you. Calibration and validation of analysis models. I think over the past 20 years we've had huge advances in nonlinear analysis, and in fact the limiting factor now is to the degree to which we trust and validate those. So this provides important data for that, as well as performance-based earthquake engineering in general. This also represented a capstone project for about 20 years of research from folks around the world, a lot in the US and Japan. And then a key thing here is to fully demonstrate the reliability for high seismic zones, because getting these building code provisions used in high seismic zones, people do that slowly. We're kind of steeped in tradition. Tests like this help to accelerate that process. So this shows an elevation view of the frame. It was designed per the 2003 provisions of the IBC, which essentially are kind of the current standard we're using in the US. A couple of features of the frame I wanted to show was that we did this with a precast construction, being as it's a low-rise frame, and also it turns out that the contractors in Taipei actually used a lot of the Japanese practice and were comfortable with the precast. On the precast system, we spliced the columns, as shown at these locations here, following practice that had been done in Japan. We often get column hinges at the base, so making sure we get that splice a little bit away from those. But in fact, at these other locations, because we have a strong column provision, we tend to not get much hinging here, and so it's more convenient in terms of construction. So we wanted to design this building as the kind of the minimum code provisions and the most daring construction provisions, so we put these splices there. if something could go wrong, we wanted it to go wrong in this test to demonstrate that we were testing the most extreme conditions. And these are our beam column, or the beam splices, bolted moment splices. We got them as close to the column as we felt comfortable with, so as to make these precast units as small as possible, but still to get it out of the plastic hinge region. I won't summarize all the details on the design, but just to point out again, this was designed with thinking high ductility system and R factor of 8. And the resulting base shear design, and this was kind of prototype building, not too different than those SAC buildings I showed, kind of a perimeter frame system. But the resulting base shear would be about 13% of the gravity load. Again, a relatively low number, taking into account it's a moment frame and fairly flexible, and that high R value. When we looked at kind of what controlled the sizing of this frame, it pretty much went this way, that the beams were sized for strength based on the design load combination. Given the beam sizes, the columns were controlled by the strong column weak beam requirement, making them stronger to promote hinging in the beams. And then the composite joints kind of fell out of the design with the column and beam sizes established. With modest detailing, we're able to get that joint connection to work. And it turned out on these low-rise systems, the drift was automatically satisfied. We don't have to add material for stiffness. Now, I have a few slides just to show the construction sequence. Now, I realize we're at a steel conference, but they did tell for these professor things that we could talk about whatever we wanted. But I just didn't do it to antagonize if there's any fabricators in the audience. But I really want to make the point is this aspect of these composite structures, like why are we talking about all this concrete at a steel conference? Well, there's a lot of steel fabrication here. Some of it is steel reinforcing bars that we don't normally think of things that steel fabricators fabricate, structural steel. But I see, again, big opportunities in trying to take systems like this, which we now view as kind of steel construction, concrete construction, and if you think of doing these things combined, I think it's a win-win situation. And so as I look at a plant like this, when I look at some of the operations going in here, aside from the casting of the concrete, it looks more like a steel fabrication shop than a precaster. So I think there's kind of great opportunities for folks in the steel industry who want to venture a little bit out, as the designers did back in Texas. So those units are precast, they're brought out and set up like this with the grouted connections down here, some temporary bracing. Steel beams are brought in, bolted. Okay, this shows the frame kind of going up in the laboratory. Now this loading beam is installed. You wouldn't have this in a building, but I point this out because the way we introduce loads into this for our lateral loading is we wanted to drag them into the frame as they would occur in a building. So we have these loading beams which we're going to push on that are connected to the concrete slab, which then deliver the load to the steel frame, steel members that are part of the frame, and into the columns. So we wanted to try to represent the real conditions as close as possible. This shows grouting of the first floor splice. So if we compare that to a welded column splice, I don't know which is easier. And then this shows the last two floors being put up. So this is the final specimen put together with some outer plane bracing. 3 sets of large actuators. These are each 3 times 1,000 kilonewtons. 1,000 kilonewtons, about 250 kips. So 3 of those required at each floor to push this frame to simulate the effects of an earthquake on it. In terms of simulating the effects of the earthquake, we loaded this what's called Pseudo-Dynamic testing method. So if you remember from school, the equation of motion, mass times acceleration, damping times velocity. This is the restoring force of the structure, stiffness times displacement, that's equal to ground motions. We wanted to simulate this in the laboratory. That is, we didn't want to presuppose how the building would be loaded. We wanted to put a ground motion on and see how the building would react. So we do this through the Pseudo-Dynamic test method. So the idea is we take our 3-story building and represent that what's important are the masses at the floor and the displacements at the floor. We could condense the many degrees of freedom down to that. We're then going to simulate the mass, damping, and ground motion effects in the computer that's going to control our loading in the lab. So if we look at the ground motion effects, we're going to put accelerations, recorded accelerations from real earthquakes into it. And the mass and the damping effects we're going to handle in the time series Newmark integration. So the only part where the structure comes in is normally where we have stiffness times displacement. What that really gives us is the restoring force provided by the structure. Now the idea here is that we're pushing on the structure with large actuators, so we know what the structure is resisting at any point in time, and we can measure that directly. So the idea is that the way we'll load the structure, we'll define a ground motion push the button on the computer to start to do the time history integration, and the displacements will be applied to keep equilibrium. And the feedback is we're going to push on the structure, measure the resulting force, bring that back in, and seek convergence in the solution here. And this is kind of a standard method that's been used probably for about 15 years or so, again, where we can't put the structure on a shake table, but to simulate the dynamic effects. So the next question is, well, which ground motions do we pick? So we picked, this was a kind of a bilateral project, so we picked one from the Chi-Chi earthquake in Taiwan and one from the Loma Prieta in 1989. And we subjected the building to 4 earthquakes, one where the earthquake ground motions were scaled to represent a more frequent earthquake, one that has a 50% probability in 50 years. So in this case here, the Chi-Chi record is actually scaled up by a factor of 1.2 to represent that condition. This points out that many of our recorded ground motions, in fact all these recorded ground motions, had to be scaled up to represent, say, the 500-year, the 10% and 50-year earthquake, our design earthquake, pointing out that we haven't seen, our buildings have not experienced a lot of what we see as our code earthquakes. We've had some big earthquakes, but not as big as what we're anticipating in our code as collapse prevention and design values. And so we had 3 levels: the frequent earthquake, the design value earthquake, 2% in 50 years, sometimes we call it the maximum considered earthquake, and then one following that just to see the residual strength of the structure. And then we're going to do a final pushover analysis to see if there's any life left in the structure after going through these earthquakes. So this plot shows, condensed in a compact form, what happened to the building. So over time, this is 160 seconds of those 4 earthquakes. This took about a week, so the pseudo-dynamic, what's pseudo about it? It's not real time. But we're going to apply the 50% chance of exceedance in 50 years. So this is what happened to the building. This is the displacement trace at the roof of the structure. But then if we're interested in kind of some metric on how the structure behaved, we can track that the building went out to, this is the interstory drift ratio for the 3-story building. So in this event, we had a maximum 2% interstory drift ratio. And this was the forces that are developed, shear forces in the columns and beams in the frame. We then move ahead and now the structure is a little bit damaged, we subject it to the 10% and 50-year earthquake. This is our kind of, quote, design value, the 500-year earthquake. And you can see here it got out to 3% maximum drift in the first floor. And you start to see the forces saturate because, of course, by this point the structure is yielding, so it's beyond its yield point. It doesn't pick up much force, but it's subjected to more deformations and more damage. Next earthquake is the 2% in 50 year. This is the maximum considered earthquake, the one where we don't want to, where we say to our public that buildings, this is our maximum considered, we don't want collapse under this event, a very extreme earthquake. And this one drove the building out to 5.3% in one direction. And then finally, we subject a 10% in 50-year earthquake again. This might represent an aftershock after a large earthquake, and we see we're back at 3%. Now the fact that in the previous step we went out to a much larger deformation, and here we're back at 3%, shows that this structure has some robustness, some remaining capacity left. So now if we look at what parts of the structure looked like at this point, not much damage at all happened during the first earthquake, that serviceability one, even though it went out to 2% drift. There's some flaking of whitewash that we painted on, but otherwise you didn't see much damage in the structure. An interesting kind of side note is you heard loud banging during it from the slipping of the bolts, our bolted connections as we went back and forth. Very large banging. It went on for a day. Of course, in a real earthquake, that'll happen in an instant, a few seconds, which is why you hear people in earthquakes talk about the terrible loud noise. But under the 10% and 50, we started to get some damage. And this is one of the beam column joints. So you can see there's quite a bit of yielding that has occurred here in this beam. Some cracking that we've marked in the columns, but the joint's relatively intact. And then if we look at another area where there tended to be a concentration of damage, this was at the column bases, okay, where we start to get some spalling of the concrete around those base conditions. And the splice, the precast splice was somewhere up here. If we then go to the 2% and 50-year event, where we've driven the structure out to 5.3% interstory drift, so a very large drift. Here we see that same beam column joint. We start to get not just yielding, but large local buckles occurring. Now these are in spite of the fact that this is a seismically designed, so it satisfies the compactness ratios that the steel provisions have. But that just postpones buckling, doesn't eliminate it. So when we get to very large plastic hinge rotations, in this case 6%, we're getting that large buckling that occurs. And then if we look at the base of the column, even more spalling and large cracking. And one of the things I observed that as we went through all these earthquakes, indeed, even though the concrete stayed intact, it really loosened up quite a bit. And what became a limiting condition at these bases was not just getting the moment through, but actually getting shear transfer. We started to get some kind of small sliding that would occur at the base. Okay, after we did all those earthquakes, we then pushed the structure out as far as we could, which was to about 10% drift. It was kind of neat to be standing next to it while we did that. Kind of spooky too. So this shows going up one of those columns, what happened at the end. We were excited about this. We got out to 10% drift just because I'm going to show some analysis results. We often do computer analysis, and some of them predict collapses up at 10 and 12% drift, which is a huge, when you're standing next to it, it's a huge amount. We rarely see that in structures, but in fact we saw that in this one here. And as shown by this pushover load deflection plot, the structure still has a fair amount of residual strength. It still has 2.8 times the design value. Now keep in mind, this is the structure that's gone through these 4 earthquakes already, and now we've kind of pushed it. You can see the damage at the column base here, quite significant. And again, shear transfer became a real concern here. If it wasn't for the large reinforcing bars going through, I don't think we'd be transferring much shear at all. So it's the bars that we count on for flexure are really carrying the shear through dowel action at this point. If we looked at the beam column connections, local buckle is getting exceedingly much larger in the beam, although the joint is still holding together. So this is a case where, again, the joint did its job to develop the strength of the beam. Finally, the end of life for this structure, these little drops that occurred over here came from a failure in our bolted beam splices. They were out here at about this location. Now those splices we designed using capacity design provisions to develop about 40%, 1.4 times the expected plastic moment capacity here. But it just shows that at these large deformations, as we strain harden these elements, that something eventually has to give. And in this case here, it was these splice plates. So it appears sudden on this plot, but it was just a ductile rupture through those plates. Now you might notice one of the interesting things on how this building deformed is that it's we have a story mechanism or a two-story mechanism that's developed. We normally think our strong column weak beam requirements will prevent hinging in our columns, but that's really not the case. It's been borne out by analysis and studies, and here we see that that wasn't the case in this example. So we have hinging in the first floor beam, but we have hinging at the column base, which is unavoidable. But then up here, instead of having hinging in the beam, we had hinging at below the joint in this column. So we went back to look at our design provisions to say, well, will they clue us into what's happening? What's plotted up here, these are numbers that relate the strength of the columns at a joint to the strength of the beams. And according to our design provisions, we typically want this ratio to be at least 1.2. That's kind of a requirement for the strong column weak beam to promote hinging in the beams. Now, if we base it on the capacity of the steel beams and the concrete columns, we get these numbers that are shown here, all of which are well above 1.2, suggesting that we shouldn't see this story mechanism or two-story mechanism developing. When we looked at the composite strength, that is taking into composite beam action, and I point this out because in design of even steel buildings, oftentimes we'll neglect composite action. We'll say it's conservative to neglect that, but when doing the strong column weak beam design, that's not always the case. So if depending on whether the beam's in positive or negative curvature, some of these numbers change, and in this case here, in fact at this joint here, these two numbers did change. But we still see for the inner joints where the beam is half bending in positive and half in negative bending, we still get a benefit from some composite action. And we shouldn't really be looking at a story mechanism in terms of joint by joint, but if we think of summing things over a story, if we sum up all these numbers, it's still equal to 1.2, and at the first floor it's equal to 1.3. And again, our hinging occurred up here, so this gives us, the fact that 1.2 is less than that gives us some clue that we would expect hinging here. But again, I think based on our basic design guidelines, we would think that these numbers would be sufficient to prevent this sort of mechanism. So I emphasize this just because this is something that often comes up in discussion. People think we've precluded hinging in the columns by applying these capacity design provisions, but because of the indeterminate nature of how forces redistribute, that in fact you can get hinging in some columns, And now the reality is this provision of 1.2 does postpone that to occur relatively late in the process. I wanted to talk a little bit about some other things we learned from looking at the system versus the component behavior. So first looking at local buckling. When we pushed on the frame this way, we had negative buckling occurring at these locations that I've shown here that created very large local flange buckles of the type I showed to you. When we pulled back on the frame this way, the local buckles would show up here. But an interesting thing that would happen is that now this flange went into tension and those local buckles straightened out. So in fact, and I'll show a slide in a minute, when we came out and looked at the building at this point, you hardly noticed that local buckles had occurred here. They had straightened out to such a degree. Now I mention this because I contrast this with subassembly tests where because of the way we load the structures and because they're not continuous, when we start to load the structure, the local buckles tend to never straighten out. And there's evidence of that in these pictures here. So this was a subassembly test where once the local buckling occurs, it tends to just accumulate. Whereas in our specimens here, this is one of the cases that had pretty significant yielding and local buckling, and this was a joint that had straightened out on a reverse cycle. So the lesson here from this is that sometimes our subassembly tests paint the picture worse than it actually is in the real structure. Also wanted to look at slab performance. I mentioned before how we loaded this through these actuators down this loading beam and through the slab. So when we push the building from left to right, you can imagine that the force comes out of this loading beam and it gets dragged to the slab and it causes compression in the slab on this side of the column, kind of bearing on it. And on the other side, it tends to cause some tension over here. Now, when I'm pushing it this way, if I look at the moment diagram, I actually find that in this same location here, the beam is in negative bending. So the flexural action in the beam tends to put the slab into tension, but the way the load, the inertial load is getting in, tends to put it in compression. So these two things are kind of fighting against each other. And the net result is that it's helping out the slab. The slab behaved better than in the subassembly tests, where in subassembly tests we introduce the loads differently. We just put the beams into bending, so we don't have that beneficial effect of how the load actually gets into the slab. And so when we do subassembly tests of these composite beams, we often find the shear studs failing and kind of ripping off. We find large cracks in the slab, but we saw none of that in this building here. Again, so pointing out that sometimes the things we test as subassemblies for convenience in the lab sometimes tend to be the worst case scenario, and things are appreciably better when you look at the full system. I'd like to shift gears a little bit and talk a little bit about the analysis we did in conjunction with the testing. So this we did with some software that's been developed by the Pacific Earthquake Engineering Research Center called OpenSees. If you want to, if you have a lot of time on your hands and patience, you could download that and try it yourself. But the interesting thing is just over the past few years, the types of models we're using here are very quickly getting into commercial software with a lot more user-friendly interfaces. So for the beams and columns, we use these so-called fiber analyses where we just discretize the slab and the beam or the column into small fibers and assign uniaxial properties to them to simulate cracking, yielding, and so forth. We modeled the beam column joint with a spring that's shown here. And there's actually two springs in parallel, or two springs in series, pardon me, which are representing these two modes of behavior, this panel shear and vertical bearing. Even though failure will usually occur to one mechanism or the other, they both contribute deformation. So we had our model included, it was calibrated to represent both of those effects. So we thought we have a good model that's kind of capturing all the nonlinearity that would occur in the building. These are just some examples we did ahead of the time to calibrate our models. This was a column test. And this is a comparison of the test data and the measured data. This was a test done by Bersi Ballerini on a composite beam, steel beam with a concrete slab into a steel column, and again the calibration there, and calibration on some of our own tests of the composite beam column joint. Okay, so we think we put together a pretty careful model that was well calibrated to the test data. So now we're going to look through some of these time history traces again, where we look at time versus roof displacement. This is that first earthquake, the service level, we think 50% chance of exceedance in 50 years. The red curves are the analysis, the black curve is the test. And in this case here, we signed very generally good agreement between our analysis and the test in terms of hitting the peaks and the peak inter-story drift and story shears are shown down below here. We did notice a little bit later in the record, due to the cracking that occurs, is we tend to get a phase shift. The stiffness decreases, the period of the building elongates. You could see that these curves spread out a little bit. So in fact, if we go and do a Fourier transform of these, taking portions of this time history here, and early on we find the period elongated from 1 second to about 1.3 seconds during the test. But the analysis did pretty well. It also did pretty well under the next earthquake, the 10% chance of exceedance in 50 year. But when we went to the largest earthquake, this 2% chance of exceedance in 50 year, we started out with fairly good agreement in terms of hitting the peaks. Okay. But then at a certain point here, we started to get large differences. So the peak measured response I mentioned before went out to about 5% drift. But then the calculated response was only about 2% drift. Okay, so if you calculate this, it's about a 60% error in our predicted displacement, or 65%. And the reason that is that these fiber analyses I'm showing you didn't pick up this local buckling. So all the softening that occurs to this local buckling was not picked up in these fiber type analyses. And I think that's an important lesson as we start to use more of these things in practice, that the nonlinear analysis is only as good as the types of behavior and the types of failure modes that it picks up. The fiber methods we were using at the time didn't pick up this local buckling. So, and it turns out that this occurs, we also get period elongation. It turns out that our analysis works well until about 3 or 4% inter-story drift. Beyond that point is when these local bucklings get large enough that we're starting to get this divergence between the two. But 3 and 4% initial drift is still pretty far along, so it allows us to capture behavior under fairly large earthquakes, but not the most extreme ones that would collapse the structure. Now, another thing, and for those of you that aren't looked at earthquakes recently and dynamics, I'll go through this quickly, so maybe too quickly, but if you have looked at that, I wanted to point out something interesting about, I mentioned we use the pseudo-dynamic method of loading, where we choose a ground record and we subject the building to that. Now, one issue that comes up is when we choose that ground record and we scale it to represent a certain hazard event, the design earthquake, for example, we could take the design spectrum, and there's different ways we could scale records. In this case here, we chose to take this record and to scale the spectral acceleration at the first period, such that that for the record matched our design spectrum. Well, it looked good, and actually since we did this test several years ago, we've learned something about scaling ground motions. You can see one problem we had is this large bump that occurs here that tells us that if our building gets more flexible, in fact, this ground motion that we thought is representing the green line here actually comes closer to representing the purple line, which is the 2% and 50-year earthquake, the earthquake about 1.5 times the intensity. So it turns out on that first small level earthquake, our period elongated from 1 second up to 1.3 seconds. So when we started to apply the 10% and 50-year earthquake, we were actually already had a building that was at 1.3 seconds. So the way we had it scaled, we were applying an earthquake that was closer to the 2% and 50-year earthquake than the 10% and 50. Now, in hindsight, you say, well, why did you do this? But in the midst of kind of doing this test with millions of technicians around, we often have a plan and we kind of carry it out. We do some checks along the way, but this was one that wasn't obvious. So our building got hit with bigger earthquakes than we anticipated. And then when we put the 10% and 50-year earthquake on it, so when we started the earthquake here, it got pushed out to a larger point there. Okay. So in fact, we got this period shift during the 10% and 50-year earthquake. And now what this tells us is that our building was actually subjected to bigger earthquakes than we intended, but the fact that it survived okay is good news. Okay. But it does point out that when we're doing these pseudo-dynamic tests, and more importantly, as folks start to use nonlinear time history analysis in practice, choosing and scaling these earthquake records to the appropriate intensities, and it's an area we're working on quite a bit in research, is a very tricky business to say what ground motion represents the design earthquake. And of course, given the uncertainty, you want to look at multiple earthquakes. Now, for our test, we had one big specimen. We could only put one ground motion on it. I'm going to show a little bit of in a few slides hence, starting to generalize this process and do more time history analysis with multiple records, because indeed each record is different, so we want to develop some statistics which would be the appropriate measure for how a building has actually behaved in a given earthquake. Now before we get to that, I just wanted to relate the analysis to physical damage, because one of the key things about performance-based design or performance-based engineering is to say, well, if I predict ahead of time through analysis, let's say, how my building behaves, and I get some hysteresis loop like this, how do I relate this to physical damage in the components? So there's different damage indices out there. One that we had is this one that's shown here, which basically is a way, it's basically a measure of the plastic hinge rotation with deformation, straining, that's a measure of damage. But there's also a counting process involved here, which takes into account not just the peak deformation you get to, but also how many cycles you've gone through, because those cycles eventually wear out your components, and they wear out different components differently. As I showed the examples of the concrete column, it tends to wear out more rapidly than, say, the steel section. So the idea is we want to be able to process analysis, or in our case test data, through this into a damage indices. These are typically calibrated to go from 0 to 1, and then to relate these to damage to these components. And so I'll just show briefly a couple of examples of that. This is a plot of damage indice going through time. This time in this case is the different earthquakes the building was subjected to. So our damage indice here of about 0.5, we have this kind of moderate damage. We go up here to about 0.8, the damage is getting more significant, start to see the local buckling. Okay, and now you notice the local buckling here is a lot bigger than it is here. Our damage index has not gone up that far. That's kind of an area of future research. We'd like to get better resolution in these damage indices, although it's tricky because, as I mentioned, these local buckles tend to straighten out. So you might look at one joint where they've straightened out and one where it's being pushed in compression. And finally, the very extreme cases here where we're starting to lose capacity in our components. Eventually, these local buckles, if you cycle them long enough, you'll get fracture, a ductile fracture. And then, as I mentioned, you start to lose shear capacity and moment capacity in these concrete columns. But the idea is that we could take these indices, and from our 3 earthquakes, we had on average some damage indices that look like these, from 0.5 up to 0.9. We relate those to the physical condition in those components. And then equally important to the physical condition is we start to think about what kind of repairs would be necessary, because the whole thing about performance-based design is saying, okay, predicting how a building would be damaged and then relating that to how it would need to be repaired. And then the implications could be the cost of repair, could be the durations of repair. And we don't have time today to go into it, but there's a whole other talk we could give on performance-based earthquake engineering, where it's doing exactly this. It's relating our structural analysis to damage and then to these decision variables, repair costs, downtimes, and so forth. Now I just wanted to talk a couple more minutes on modeling implications. As I mentioned, we use these fiber analysis, which did not pick up the local buckling that's shown here. Now what's shown on this plot is actually, these are the 4 earthquakes we subjected the building to. One dot is our analysis data. This is interstory drift on the horizontal axis. The other dot is the measured data. So this shows that for the first 3 earthquakes, we're doing pretty well. These dots are close together. And it was with this last earthquake where we got the large difference between the two, because we were not representing this local buckling in our fiber analyses. And this points to the need to look for better sorts of models. And we've been doing research since the time of this test, where we've actually, instead of going to fiber type models, we've gone to kind of lump plasticity or plastic hinge models, which on the one hand are a cruder model. They don't track the spread of yielding through the cross section as well. But what they allow us to do is to, through these backbone curves here, to more explicitly define the rotation capacity that we'll have in these components, and when we'll start to get this strain softening behavior. In other words, when things like local buckling kick in, if it was a reinforced concrete, it could be buckling of the reinforcing bars that start to degrade the strength, because this kind of behavior is something that's right now not picked up in these so-called fiber analyses. And with models like this, what we can then do is do analyses where we go beyond looking at the behavior under given level earthquakes to scale. This we would do by analysis, is to continue to scale up the ground motions until we actually get collapse of the structure. So the slide, the plot on the left here, say if I'm at this 2 and 50 level MCE, these red dots that I'm showing here, this is the response of a building now in analysis to 10 different earthquakes. And different earthquakes affect the structure differently, even though they're scaled to the same intensity. So they'll affect the deformations as shown here. But you see here, we're out here to 4% deformations and 6% deformations. This is when the fiber analyses kind of lose their accuracy. But if we go to these lump plasticity that capture this strain softening, now calibrating those is not an insignificant effort, but we could then trust these models to go further out. We could continue to scale up our earthquakes and thereby get predictions of when the structure is going to collapse. Now this big fuzzy cloud, if you've done pushover analyses, static pushover analyses, these are sometimes we call these dynamic pushover analyses or incremental dynamic analyses. Each one of these corresponds to what would happen to a building in a time history analysis under different ground motions. As a structural engineer, the disconcerting part is you see the large variability depending on which ground motion you choose. You get a large variability in the collapse capacity. But this is the exact, but we can't get around this problem because we don't know ahead of time what the characteristics of the ground motion would be. But the way we design for it is we have to start to do statistics with these numbers. But it's kind of late in the afternoon and getting close to party time, so we're not going to go through those statistics today. See Ron's breathing a sigh of relief. But you see that this building, and this is an analysis we did of another building, not the similar, it's another 4-story building, not the same one that we tested in the laboratory, but it does show that this collapses at about 7 to 12% drift, which is not inconsistent with the fact that we took this frame, and if you remember that slide I showed where we pushed it out to 10%, the structure still had capacity, but you imagine during an earthquake it's starting to lose capacity, and this is the intensity of the earthquake, so a slightly higher intensity will kind of push it out to collapse at those drift levels. Now remember, that's a well-detailed, seismically detailed beams and columns and low-rise structure, not heavy axial loads in the columns that allow us to get out to these deformations. And I did want to point out here is that contrasting again these fiber type models with the hinge type models, the hinge models allow us to track that softening pretty well, but the trade-off is they don't track the beginning of loading as well, the initial cracking of concrete, yielding of steel. And so if we zoom in on this initial loading using these two different models, we see this is from the fiber analysis and this is from these plastic hinge analyses. The fiber analysis, this kink up here really occurs from yielding and cracking. And another aspect of performance-based design is knowing when the onset of damage is, which is very much related to drift. Okay? So this suggests that when you really want to look at the onset of damage, that's where some of these refined fiber analyses work very well. But when you want to go to collapse and you're capturing things like the local buckling, you want these hinge models, but these hinge models don't typically capture the effects well at the low levels. Okay. Now hopefully someday programs will have both things built in, so you could say fiber analysis, hinge model, so as an analyst maybe it'll be easy to switch between these two, but we're currently not to the point where one model does it all. Just to kind of wrap up this, the analysis, kind of a follow-on to the study we did here, is with some of the data now and the analysis models that we've calibrated and validated, we went back and we designed 3 buildings. I showed you the 20-story design before, and just to subject this to using our analysis program to try to make predictions of behavior. Okay, so we took the 3, 6, and 20 perimeter frame designs, and I'll just show you the results for the 6-story frame. So this is the spectral acceleration. These are different earthquake hazard levels. We subjected this to 20 earthquakes, and at each stripe of data here, these are these 20 ground motions that are scaled to a consistent hazard level. So for example, the 10 and 50 level is here, and the 2 and 50 level is up here. Typically, we'll do different ground motions. You can see this is a very damaging ground motion. This one's a not so damaging. So typically, we'll do statistics. Oftentimes, building code provisions will look at the median values and say, what are the drift levels? So if we look at this case here, at the design level, in fact, the 6-story building is performing just as we expect within the 2% drift limits that codes prescribed. And if we go to this 2 and 50 level, even in this case, the worst ground motion, but in particular, especially the average one, is well below this 4%. So these results here were calculated with this fiber analysis, which is not capturing the local buckling, but it's showing at least up to the levels that we're looking at here that a code-conforming building is going to behave well under these very large earthquakes. And this is for the 6-story building in general. We found the same thing for the 3 and the 20-story buildings. So some quick observations that, again, both the analyses and tests we did in the lab, we designed the test to be at the minimum limits of the current building code. Sometimes buildings have a little bit of overstrength, but we've purposely pushed everything to the limit. We located the splices in the worst points and everywhere. But the building behaved very well. The composite joints held up, composite beam action was maintained, the precast column and the beam splices performed well. Again, we got that beam splice at the very end, but that was out past 10% drift. The strong column, weak beam, it's important when you do that check to consider composite beam action because you could get quite different values. And the typical ratios we use, they tended to make the building perform pretty well, but it doesn't necessarily preclude hinging in the columns and those mechanisms, multiple story mechanisms developing. These nonlinear fiber analyses worked up to about 3% drift ratios. They were accurate. Above that, again, we started to get inaccuracies due to effects such as local buckling that were not captured. I talked about the importance of appropriate ground motion selection and scaling. In our case, it was a case of doing a pseudo-dynamic test in a lab, but I think in looking to the future as nonlinear time history analyses get used in practice, this is going to become a more and more important issue to pay attention to. And then the last point on the testing was that the full system versus the subassembly testing, the key message there is that sometimes our subassembly tests behave much worse than the real structure might behave due to those effects, the slab effects that I talked about and so forth. So I think that's an important lesson, especially for the researchers in the audience, for all of us to keep in mind about when we do subassemblies, there's only so much we can do to replicate the real conditions, but to be very mindful of what we're capturing and what we're not. Future research and development, and then I'm going to wrap up with a few slides of looking at some modern buildings being built. I think there's, as I've said a few times here, there's a lot of opportunities to develop cost-effective erection construction methods, especially for low-rise. A lot of opportunities to kind of innovate this basic composite idea through different kinds of erection elements, kind of really thinking of reinforcing bars in concrete as maybe a type of fabricated steel. On the research side, a lot of room to improve our models to capture large deformations. Quite a bit of work going on, and you'll see code provisions coming out. There's a large project by the Applied Technology Council on performance-based assessment methodologies that really standardize how you take nonlinear analysis methods, scale, and get predictions of the performance of the structure. And I guess continuing to innovate new systems. Now I want just to think about the new frontier, and I mentioned at the outset that I think a lot of this composite systems got their impetus from the fact that they were developed in Texas at a time. There was a lot of construction going on. It was kind of young city in terms of building codes and in terms of trades and so forth. Fabricators were excited about working on these systems. And that development occurred over about 10 or 15 years that kind of pioneered these composite systems. So where's the new frontier? I emailed some of my colleagues who were out in practice, and I got a few back, in particular from Skidmore, Owings & Merrill, who's doing a lot of work in China these days. And if you've traveled to China, you know the kind of, it makes Houston in the 70s look like kids play, right? But these composite systems being used there, this is a particular 67-story, the Nanjing Financial Center. I think if you contrast these to what we were doing in the 70s, there's a few things going on. Buildings are getting taller. The architecture is getting more daring, the configuration. There's also a lot of mixed use, whereas a lot of the buildings that I showed from Houston were office buildings where you have certain floor heights and tenants and so forth. A lot of these are mixed use where they might go to office, to hotel, to residential. So interesting design challenges. This particular one uses a concrete core supplemented by a composite moment frame of the kind I've been describing, reinforced concrete columns, steel beams, along with belt trusses and outrigger trusses to get these things all to work together. The reason they're using this is a lot of the same reasons we saw in the earlier frames. The use of reinforced concrete columns and compression, more economical than steel. Also in this case, it pointed out that the differential shortening, the fact that both your perimeter elements and your wall are concrete, it helps out with the differential shortening. Of course, you need to think about the stress levels in those columns. This shows a plan view of the framing system, again the perimeter frame around the outside. And this is one of the beam column connection details. Not that different. There's a steel erection column in here. You see though the big beam goes continuous through, face bearing plates, shear studs. These are rather large columns. And then the erection column gets interrupted, and this is built in a tree type of construction like some of the slides we saw earlier. This is just another building in Beijing that uses really a very similar system. And yet another one that has another kind of perimeter frame concrete core. And these are actually sloping columns, and these are actually using composite columns in this case here, where they have about 6 to 8% area of structural steel, 2.8 to 3.5% reinforcing bar steel. So I show these as just examples of kind of how these systems continue to evolve and be innovated, although of the systems that we're seeing here, it's still conventional in terms of the basic concepts that were started 20, 25 years ago. The question, or the point I guess I'll end you with, is innovation's closer to home. Those of you from the West Coast, and I think it's happening in other places as well, there's been a lot of urbanization that's been happening. We kind of think the city is as dense as it can get. Particularly a city like San Francisco, that's a lot of low-rise building, has about 30 or 40 high-rise buildings, the highest of which is up at 1,000 feet. On the books are being planned, and this is being planned thoughtfully for downtown development to kind of optimize services, preserve green spaces and things like that. So I think there's a lot of kind of urban societal challenges that buildings of different heights can face, and I think it's up to us to be thinking to ourselves how to innovate and do things better. It's not always easy, as folks in practice know, because it's easy to do what you did last time, but I think from taking small steps on projects that over the years will kind of innovate into things we don't imagine at this point. So with that, I'd like to thank you for hanging out here today and see if there's any questions